An average is a number which best represents a set of data. There are three types of average: the mean, the mode, the median. The mean is obtained by adding up all the numbers and dividing by how many there are. For example, marks in a test out of 10 equals 46 over 10 equals 4.6. If all the marks awarded were shared out equally, the mean is how many each person would get. So, in this example, each person would get a mark of 4.6. The mode is the number which appears most often. For example, in this set of numbers, there is 1 2, 2 3s, 1 4, 4 5s, 1 6, and an 8. So the mode equals 5. If there is no one number that appears more often than the others, then there is no mode. For example, in this set of numbers, there is no mode. The median is the middle value when numbers are placed in order. For example, in this set of numbers, the median is 4. If there is an even number of values, then the median is the number halfway between the two middle values. So the median of the figures above is halfway between 5 and 5. So the median equals 5. Or for another set of figures, the median is halfway between 2 and 3. So the median is 2.5. The range measures spread. It is the difference between the smallest and the largest values in a set of data. So in the set of data above, range equals 8 minus 2, which equals 6. Scatter graphs are used to see if there is any connection between two sets of data. If there is a connection, then we say there is a correlation between the two sets of data. For example, the table shown here gives the marks scored by 10 pupils in a French test and a German test. In scatter graphs, we let the horizontal axis show one set of data and the vertical axis the other. In this example, we show the French scores on the horizontal axis. Each pair of French scores and German scores are used as coordinates to plot points on the graph. The points on the graph are close to being along a straight line. This suggests that there is a relationship between the pupils' French scores and their German scores. Scatter graphs. The table above shows the number of visits to a cinema by 10 people in a month and the distance they live away from the cinema, shown in kilometres. This table shows the height of 10 pupils in metres and their scores out of 50 in a maths test. If you think there is a connection between two sets of data, then you can plot the points on a scatter graph and look to see if they are nearly along a straight line. Note carefully, don't join the dots together. The closer the points are to being on a straight line, the stronger the correlation is between the two sets of data. Consider the French and German scores example. We can see that the German score increases as the French score increases. This is called positive correlation. When the correlation is positive, the points seem to go up as you read from left to right. If one amount increases while the other decreases, we say that there is negative correlation. Here the points seem to go down as you read from left to right. If the points do not lie close to a straight line, then we say that there is no correlation between the two sets of data. An example could be pupils' scores in a maths test and their shoe sizes. In most cases, there will not be a straight line which passes through all the points, but you will be expected to draw by eye a straight line which passes as close as possible to all the points. A line which is drawn to pass as close as possible to all the points is called a line of best fit. The line of best fit must pass through the points plotted, representing the means of the two sets of data. NB, if there is no correlation, then we will not be able to draw a line of best fit. It is possible to use a scatter graph to estimate one piece of missing data if the other is known. For example, in our French-German class, one pupil may have been absent for German but present for the French paper. If this was the case, because there is a correlation between the two sets of figures, it is reasonable to estimate what the pupil might have scored in German. This can be done by using the line of best fit. So let's say a pupil scored 45 in French, By drawing a straight line to intersect the line of best fit and then reading off the German axis at that point, we can estimate that the pupil would have achieved a German test score of 43. When there are many items of data, it is easier to use a frequency table. Example: a class of 18 children sit a mental arithmetic test. The frequency table shows their marks out of 10. We need to find A, the mode, B, the median, and C, the mean mark. The mode is the value which occurs most often, so the mode is the value with the highest frequency. The mode or modal mark in this example is 8, as more children had a mark of 8 than any other number. The median is the middle value found by arranging the data in order of size. As there are 18 items of data, the median is between the 9th and 10th values. So in this example the median is 8. Alternatively, you could find the 9th and 10th values from the frequency column. To find the mean mark, we need to know A, the total marks of the class, B, the number of children, that is, the total frequency. Adding a third column to the table helps us to do this. The values in the third column are found by multiplying the numbers in the first and second columns. If data has a wide range of values, it is often easier to use a grouped frequency table. For example, a class of 20 pupils sat a maths exam. The frequency table shows their marks out of 50. This row tells us that 4 pupils had between 21 and 30 in the exam. Notice that we do not know the pupils' exact marks, so A. We can't find the exact mode from this table, but the modal group is 41 to 50. B. We can't find the exact median value from this table, but we can say that the median is in the 31 to 40 group. C. We can't find the exact mean, but we can estimate its value. To do this, we need to add another column, the midpoint column, and then we continue as usual. 45.5 is halfway between 41 and 50. That is 41 plus 50 over 2, which equals 45.5. So we can assume that all 7 pupils scored this mark, because we have to assume that they are equally spread out within the group. Estimate of the mean equals estimate of the total marks divided by the total frequency, which equals the last column total divided by the third column total, which equals 639 divided by the 20, which equals 32.0 to 1 decimal place. We use frequency diagrams to display data from a grouped frequency distribution. The data is displayed as a bar graph. The height of each bar represents the frequency of each group. For example, the following grouped frequency distribution shows the heights of 30 pupils in a class. In the group 130 to 135, the pupils are between 130 centimetres and 135 centimetres tall, but not exactly 135 centimetres tall. Here is a grouped frequency diagram of the data. We can see that the group with the highest frequency is the 140 to 145 group. We call this the modal group or the modal class. Let us look again at the distribution of pupils' heights. The points are joined together to form a frequency polygon. NB, don't join the points to the bottom axis. To work out the cumulative frequency of a group, we add up all the frequencies so far. Example, the heights of 50 plants. The final cumulative frequency figure will be the total frequency, 50. By working out these values, we are putting our data into ascending order. We can say that overall, the 6th plant will be the tallest in the group. X is greater than 0 and less than 10, so we can say that its most likely height will be 10 centimetres. The 18th plant will be the tallest in the group. X is greater than 10 and less than 20, so we can say that its most likely height will be 20 centimetres. If we assume that all the heights between are evenly spread out, then we actually plot estimates for heights of plants. This is called a cumulative frequency diagram. The cumulative frequency up the left-hand side can be thought to represent each plant from 1 to 50 in ascending order. The median is the middle value when the data is arranged in ascending order. As a cumulative frequency diagram puts the data in order, we simply read off the middle value. In our example of 50 plants, the median will be the 25th plant. Remember that the individual heights are not known, so the median will be an estimate. The lower quartile is the value 1/4 of the way into the distribution, that is, a quarter from the bottom. In the plant example, the lower quartile is 50 divided by 4 equals 12.5 value. Reading off the height scale gives lower quartile equals 15.5. The upper quartile is the value 3/4 of the way into the distribution, is 37.5 the value. 50 divided by 4 times 3. Reading off the height scale gives upper quartile equals 30.5. The interquartile range is the difference between the upper quartile and the lower quartile. It gives us the range of the middle half of the values. IQR equals UQ minus LQ, which is 30.5 minus 15.5, which equals 15.